Welcome to our Quantum Deep Dive, where we take complex topics and try to break them down into digestible, fascinating insights. Today, we're embarking on a journey into the really exciting, cutting-edge world of quantum technology. We're focusing on one truly pivotal figure, someone whose groundbreaking work, well, it fundamentally changed the field. You've shared this brilliant essay with us on Vladimir E. Manucharyan, written by Yurigo Schneepat. It's a fantastic look at how, one scientist can really alter the whole trajectory of a scientific discipline.
Indeed. And our mission today really is to unpack Manucharyan's incredible scientific development, his significant contributions to superconducting quantum architectures, and particularly his pioneering work on something called the Fluxonium qubit. We'll explore why his innovations aren't just like theoretical breakthroughs on paper, but practical game changers for quantum computing and, frankly, beyond.
So what does this all mean for you, the curious learner tuning in? We're going to give you a clear, concise overview, hopefully, of the core ideas, the surprising challenges he overcame, and the lasting impact of this one individual on the ongoing quantum revolution. Okay, let's dive in. Let's maybe start right at the beginning. Who is Vladimir Manucharyan, and what sort of shaped his early scientific journey?
Right, so Vladimir Eduardovich Manucharyan was born back in 1982. In the Soviet Union. Mm-hmm. And as the essay points out, this was an environment really renowned for its incredibly strong mathematical and scientific traditions. His early schooling quickly showed he had this remarkable excellence in math and physics, which led him to the prestigious Moscow Institute of Physics and Technology, or MIPT. Mm. And that rigorous theoretical foundation, influenced by legendary thinkers like Landau and Lifshitz, it was absolutely crucial for his future work.
Okay, so he had this fantastic grounding from the start. But what specifically sparked his interest in quantum phenomena? What pushed him towards this, cutting-edge field?
Well, it was the early 2000s, and quantum information science as a field was really just emerging, really taking off. Manucharyan was drawn to these really fundamental concepts like entanglement.
Where particles are linked.
Exactly. Mysteriously linked. And superposition, a quantum bit being both 0 and 1 at once, and coherent states, which are like these super-organized quantum waves. He quickly grasped the immense potential of bridging that abstract world of quantum physics with practical engineering. Specifically, he saw how superconducting circuits.
Right, those materials with zero resistance at low temps.
Precisely. How they could be harnessed to create functional quantum technologies. He really focused on understanding how energy states become quantized, like distinct steps in these tiny components called Josephson contacts, and how complex connections behave in these superconducting networks.
That's where it gets really interesting. How did he make that leap from deep theory to actually building these things, becoming a pioneer in experimental quantum physics?
Right, so after MIPT, he made a pretty bold move. He decided to move west, and he was specifically aiming for a top experimental quantum physics group. This ambition led him to Yale University for his PhD, and there he found really the ideal mentor in Michel Devereux, who's just a central figure in modern superconducting quantum physics. That period at Yale was absolutely pivotal. It laid the hands-on groundwork for what would become his most famous contribution, the Fluxonium qubit.
Okay, so he's at Yale working with the best, but what were the big problems facing quantum computing at that time? What challenges did he set out to solve?
Well, the early superconducting qubit designs, things like the charge qubit and later the transmon qubit, they faced pretty significant limitations. Imagine trying to use a super delicate scale, but the room is filled with static electricity you can't see. That was kind of like the charge qubit, highly sensitive to random static charges, these offset charges.
Which makes holding that quantum state really hard.
Incredibly difficult, yeah.
Yeah.
Now, the transmon qubit, it did reduce that sensitivity quite a bit, but both still struggled with two key issues. Mm-hmm. Coherence, how long the qubit could actually hold on to its quantum state.
Right.
And just general resistance to noise, all those tiny environmental disturbances messing things up. So the challenge was clear. How do you design a superconducting system that just isn't bothered by these random charge fluctuations? How do you get more stable quantum states?
And his dissertation, Fluxonium, single Cooper pair circuit free of charge offsets, sounds like it was aimed squarely at that problem. So what was the core idea behind Fluxonium? How did it tackle that challenge?
Yeah, the ingenuity here is really something. Fluxonium is based on a superconducting ring. With a single Josephson junction, that crucial quantum switch component. But, and here's the critical twist, it's shunt, coupled through a large inductance. Think of an inductor storing energy in a magnetic field. Manucharyan used a special type, often realized by a whole chain of many, many tiny Josephson junctions acting together as a superconductance. And this fundamentally changes the energy landscape of the qubit.
How so?
Well, the Hamiltonian, which describes the system's energy, it gets this new term related to the phase variable quadratic term. Basically, instead of like a shallow dish where the state can easily get knocked out, this structure creates multiple, much deeper energy minima or valleys. Imagine shaping that valley so a marble, the qubit state, sits way more stably and predictably in one of these pockets.
Ah, I see.
This re-engineering allowed for incredibly stable, controllable quantum oscillations, much less susceptible to that outside interference.
That sounds incredibly precise to build. How did they actually manage it in the lab? And, well, what kind of performance did they achieve?
Yeah, the experimental side needed truly incredible precision. Typically using aluminum on sapphire or silicon, etched with microscopic accuracy. The biggest hurdle, really, was manufacturing that superconductance, making dozens, sometimes hundreds, of tiny Josephson junctions that were all perfectly homogeneous.
A single flaw could ruin it.
Exactly. Even a slight imperfection could cause decoherence, loss of quantum information. They also needed microwave resonators, tiny antennas, essentially to read out the qubit states without disturbing them. That's the circuit QED approach.
Like peeking without touching.
Precisely. Non-invasive readout.
And the payoff, did it really help with that noise problem they were fighting?
Yes, significantly. The Fluxonium design specifically minimized sensitivity to what's called 1F noise, that pervasive low-frequency static, like a background hum.
Right, the tricky stuff.
Yeah, and this led to remarkable coherence times. So think of T1 as how long the qubit holds its energy, like a battery charge. T2 is how long it keeps its quantum information before the environment scrambles it. Manucharyan's team got T1 times around 300 microseconds, and T2 decoherence times between 100 and 200 microseconds.
Wow, okay. That's a huge leap from what was before.
Monumental. It made these qubits stable enough to genuinely consider for practical quantum computers. It put them right up there with other leading technologies like ion traps in terms of coherence.
So, connecting this to the bigger picture, then, what does this improved stability and control really mean for the future of quantum computing?
Okay, yeah, the bigger picture. Fluxonium offers several really key advantages over, say, the earlier transmon qubits. You get higher control over the transitions between the qubit states, so more precise manipulation. It operates at lower frequencies, which inherently reduces some types of high-frequency noise. And critically, it offers better separation between the logical states, your 0 and 1, and any unwanted excited states.
And that separation is important. Why?
It's crucial for implementing high-fidelity quantum gates, the basic operations and quantum algorithms, and especially for the ultimate goal of quantum error correction. You need clean operations. In fact, Manucharyan's team demonstrated a fundamental two-qubit gate, the controlled Z, or CZ gate, with an error probability below the threshold needed for surface codes.
That's a major error correction scheme, right?
Exactly. So that was a huge step towards building reliable, fault-tolerant quantum computers.
Okay, so the Fluxonium qubit itself, clearly groundbreaking. But Manucharyan's influence, as the essay highlights, it went beyond just designing a better qubit, didn't it? What else did he contribute?
Absolutely.
Yeah.
His work had a profound impact on quantum metrology, the science of making incredibly precise measurements. Because of Fluxonium's unique energy structure and high coherence, it turns out to be ideal for detecting tiny, tiny changes in external fields, like magnetic flux or electric voltage.
How sensitive are we talking?
We're talking about detecting flux changes as small as like 10 to 6. That's a millionth of a magnetic flux quantum. This level of precision was previously really only seen in specialized devices like squatos, but Fluxonium can potentially do it with even lower noise. It opens up new avenues for fundamental physics and sensing.
And he also looked into quantum noise itself, right? Understanding and controlling it.
Yes. He and his team investigated very rigorously how these superconducting qubits interact with their environment, how they lose energy. They found that certain noise sources, like these tiny defects in the materials, called two-level systems, or TLS, could actually be suppressed or maybe even channeled away depending on their frequency. They used fundamental quantum mechanics, specifically Fermi's golden rule, to basically predict how qubits lose energy. And this understanding led to this really useful concept of quiet frequency windows, basically finding specific frequency ranges where you can run your quantum operations with minimal interference from the environment.
Like finding a clear channel on the radio.
Exactly like that.
Okay, and what about connecting these super sensitive qubits to the outside world? That seems like a big challenge too.
It's a huge challenge. How do you read the state without messing it up? His research really advanced how coupling qubits with classical microwave resonators allows for what we call quantum non-demolition, or QND, measurements.
Peaking without destroying the quantum state.
Right. And what's called the dispersive regime, the qubit state subtly shifts the resonator's frequency. You detect that shift, and you know the qubit state, but you haven't destroyed the fragile quantum information itself. This QND capability is absolutely fundamental for any kind of repeatable operation, and especially for error correction down the line. And beyond readout, he also made big contributions to the precise timing and control of quantum operations. By carefully choosing system parameters, his team could precisely generate and shape the quantum oscillations.
Enabling better gates.
Exactly. Enabling high-fidelity quantum gates. This involves concepts like operating at sweet spots, where the qubit is naturally less sensitive to certain types of noise, and using optimized control pulses, like these specially shaped microwave signals called DRAG pulses.
DRAG.
Derivative removal by adiabatic gate. It's a technique to guide the qubit very precisely to the state you want, minimizing errors and preventing it from leaking into unwanted energy levels. Really sophisticated control.
Manucharyan clearly built an incredibly strong foundation. How did he then integrate into the wider quantum community? And what's his lasting legacy looking like?
Well, his career is really a prime example of how crucial interdisciplinary collaboration is in this field. He worked super closely with other pioneers, like Michel de Boret at Yale, of course. But later, he collaborated with people like Rainer Blatt, who's famous for ion-trap qubits, and John Martinis, who led Google's big push on scalable superconducting processors. He also had exchanges with theorists like David DiVincenzo, who kind of set the benchmarks for quantum computing. He got involved in major international initiatives, too, helping connect research efforts across different groups and even continents.
So definitely not a solo act. He was a key player in this much larger ecosystem, pushing the whole field forward. What about his contribution to quantum information science, QIS itself, maybe beyond the hardware?
Yeah, in QIS, he provided both theoretical ideas and the experimental validation for them. He developed new protocols for high-fidelity quantum logic gates, really uniquely combining ideas from quantum optics, nonlinear dynamics, and condensed matter physics. And beyond his own research, he's deeply committed to training the next generation. At the University of Maryland now, he's mentored numerous PhD students and postdocs who've gone on to leading roles themselves. His courses, his open access resources, things on software platforms like QTEP and Qiskit, they're widely used by students and researchers everywhere.
That's great.
And what's also fascinating is his impact on actually industrializing and scaling up these systems. His work on things like multi-layered 3D integration, using different materials like crystalline silicon that's directly relevant for companies like IBM, Google, the ones building large-scale quantum systems. He's also actively involved in standardization efforts, with bodies like the IE and the U.S. Department of Energy. That's crucial work for building a real quantum industry.
And he managed to make this incredibly complex topic more accessible somehow.
Yes, I think so. While Fluxonium, started as maybe a niche academic concept, Manucharyan really worked to make its potential clear through very structured publications, through open science, like sharing design files on GitHub.
Oh, really?
Python scripts, things like that, and through dedicated workshops. So today, Fluxonium isn't some obscure idea. It's in university courses, it's in textbooks, it's considered a reference architecture.
That all points to a huge impact. Has there been formal recognition for all this?
Oh, yes, definitely. He's received numerous major awards, the NSF Career Award, the Sloan Research Fellowship in Physics. He was named an APS Fellow for his contributions. And his work has been repeatedly recognized in top publications, Physics World, Nature Highlights, Science Editor's Picks, often named among the top 10 breakthroughs in physics. That really highlights his central role. Plus, he serves as an editor for journals, reviews papers, advises major initiatives, really shaping the direction of the field.
It's absolutely clear that Vladimir E. Manucharyan isn't just, another scientist. He's a true pioneer who has profoundly shaped the future of quantum technology. That blend of deep theory and experimental skill is really inspiring.
Indeed. His work on the Fluxonium qubit, it's laid such a vital foundation for what comes next in the quantum revolution, which is, moving beyond just demonstrators to truly fault-tolerant, scalable quantum architectures, the kind that can actually achieve practical applications. And his other contributions to metrology, understanding noise, integrating systems, they're just as crucial for building the precise, reliable quantum systems we need.
Manucharyan's legacy is obviously immense, but science never stands still. Building on his work, what are some of the really big questions, the next big mountains to climb for quantum researchers today?
Right. That's the key question now. A few big ones come to mind. How can these Fluxonium qubits be integrated into really large-scale, fault-tolerant networks, thousands or millions of qubits, without losing that precious coherence or becoming just impossibly complex to control?
The scaling challenge.
The massive scaling challenge, exactly. And related to that, how can the manufacturing of these specialized superinductances be industrialized? How do you go from lab-scale precision to mass production without compromising quality? That's a huge engineering problem. Then there's the material science side. What alternative materials or maybe different 3D architectures could push the performance of Fluxonium systems even further? And finally, something that's really burgeoning now is the integration of machine learning, using AI to help control and optimize these incredibly complex quantum processors. That's a really exciting intersection right now.
These are definitely profound questions for the future of quantum tech. It's really exciting to imagine how scientists, inspired by pioneers like Vladimir Manucharyan, are going to keep pushing those boundaries. Well, that's all the time we have for our deep dive today. We really hope you enjoyed this exploration into the world of superconducting qubits and the work of a key figure. Thank you so much for joining us.
And we definitely encourage you to explore the source material further from Jurgo Schneppat. You can find it available at schneppat.de. Goodbye.